Chapter 12. Conversions and Equivalents.
Next, we turn to length conversion.
This is the length conversion table from the first part of Chapter 12, Conversions and Equivalents, of the Control Valve Handbook. This table is a matrix-style conversion chart designed to convert various length units such as meters, inches, and feet. For example, to convert meters to inches, multiply by 39.37, and to convert to feet, multiply by 3.2808. Other units are converted in the same way. Please find the starting unit in the row and the target unit in the column, then use the multiplier at the intersection as the multiplication factor. I encourage you to use this to quickly find and apply the values needed in your practical work.
This table is a reference material that summarizes the multiplication factors required for conversion between various length units. For example, to convert inches to meters, you multiply by 0.0254, and to convert kilometers to miles, you multiply by 0.62137. Rather than memorizing all the figures, please identify the base unit and the target unit you wish to convert and apply the corresponding multiplication factor. To prevent unit errors during design or calculation, I recommend accurately referencing the conversion ratios in this table whenever necessary.
This table contains the principles of conversion within the metric system and the exact conversion values between inches and millimeters. Metric units can be converted simply by adjusting the decimal point, and calculations are based on the exact value that 1 inch equals 25.4 millimeters. For example, 1 millimeter can be converted to 1,000 microns or 0.03937 inches. Other whole inch conversion values are detailed in the table, so please refer to them directly to apply the necessary figures accurately during design or practical work.
Let's look at how to use the whole inch-millimeter equivalence table. This table lists exact equivalent values calculated based on the standard that 1 inch is 25.4 millimeters, demonstrating the principle that any multiple can be accurately converted simply by manipulating the decimal point. For instance, you can immediately verify whole unit conversions, such as 5 inches, being 127.0 millimeters and 20 inches, being 508.0 millimeters. Other values are detailed up to the 100 inches range, so please find and apply the values you need from the table during design or field work.
This is a conversion table for converting fractional inches to millimeters. This table is constructed based on the standard that 1 inch is exactly 25.4 millimeters. For example, you can immediately check the millimeter values corresponding to fractional dimensions such as 1/16 in, being 1.6 millimeters, and 1/4 inch, being 6.4 millimeters. By combining the whole inch row in the fractional column, you can quickly convert any dimension, so please find and utilize the values needed for your practical work.
This table provides examples and methods for precisely converting fractional inch dimensions to millimeters. For example, 1/2 in is 12.7 millimeters. In the case of 4.5 in, which includes a whole number, it is calculated as 114.3 millimeters by adding the whole value of 101.6 and the fractional value of 12.7. Rather than memorizing all the figures, please use the table by following the rows to check the whole number part and adding the corresponding conversion value for the fractional part. I recommend referencing this table to calculate accurate millimeter values whenever a specific dimension is required in your work.
This slide is a conversion table that maps fractional inches, decimal inches, and millimeters to one another. It is based on the fundamental relationship that 1 inch equals 25.4 millimeters. For example, 1/4 in is 0.25 inches, or 6.35 millimeters, and the table includes detailed values down to fine fractional units, like 1/64 in. When performing precision machining or drawing dimension work, please use this table to quickly identify and convert values between fractions, decimals, and millimeters.
This table is a reference for cumulative millimeter values, where integer inches are added to fractional inch units. For instance, demonstrates the principle where values increase by 1 inch, such as from 4.8 millimeters to 30.2 and 55.6 millimeters, by adding 25.4 millimeters. Engineers should select the required fractional item and then follow the row to find the cumulative value within the range of 0 to 10 inches. When checking these values, we recommend caution not to round the decimal points beyond the required level of accuracy.
Continuing from the previous content, this slide contains detailed conversion values for the range from 0.44 inches to 0.52 inches. For example, 1/2 in is 0.50 inches, which is 12.7 millimeters, and 33/64 inch is 0.515625 inches, converting to 13.0969 millimeters. The table pairs these fractional units, as well as decimal inch values with precise millimeter measurements. Engineers should compare the fractional and decimal items to reference the appropriate conversion value based on the precision required for design or machining.
In this section, I would like to introduce the structure of the additional conversion table for changing inches to millimeters. The table is broadly divided into an inch section and a millimeter section, placed side by side. The inch section is further split into a fractions column for fractional notation and a decimals column for decimal notation. The text tie-in seen here is actually the end of the word fractions, which was cut off due to the column width. In other words, the structure is designed so that by reading one row, you can simultaneously compare the same length in fractional inches, decimal inches, and millimeters.
This table serves as reference data for converting fractional inch units to millimeters based on the standard relationship of 1 inch equaling 25.4 millimeters. For example, 1/8 inch is 0.125 inches, which corresponds to 3.175 millimeters. All values are listed very densely at 1/64 in intervals, so when designing or machining, please find the required fractional value first, and then check the corresponding decimal and millimeter values. For actual application, we recommend rounding the decimal points appropriately to match your work precision.
This part represents the header for the continuing section of the inch to millimeter conversion table we saw earlier. The fraction seen here is the column title for fractions, split into 2 lines within the cell. The table continues in a repeating format of inch and millimeter sections, allowing you to read the fractional inch, decimal inch, and corresponding millimeter values together in one row. Understanding this header structure ensures that you can quickly find conversion values without confusion when converting inch dimensions written as fractions on a drawing to millimeters in a design or machining environment.
This slide is a fractional inch conversion table based on the standard relationship that 1 inch equals 25.4 millimeters. For example, 33/64 is precisely converted to 13.0969 millimeters, and 5/8 is converted to 15.875 millimeters. The table includes detailed entries from fine fractions of 1/64 of an inch to their corresponding decimal inch values. Rather than memorizing all the figures, please use this as a reference to find the necessary dimensions during design or machining, and convert them to the exact millimeter values.
Next, we turn to area and volume.
This slide is a reference table summarizing conversion factors between various area units. The principle is to multiply the original value by the multiplier found at the intersection of the row for the unit you are converting from and the column for the target unit. For example, when converting square meters to square inches, multiply by 1,549.99, and when converting square miles to square meters, multiply by 2,589,990. Please refer to the table directly for other values as needed for practical design or calculations.
This slide is a volume conversion table based on cubic decimeters or liters. Similar to the area table we looked at previously, it works by applying the multiplier at the intersection of the row and column to convert units. For example, multiplying 1 liter by 61.0234 gives you cubic inches, and conversely, you can convert to liters using 28.317, which is the first value in the cubic feet row. The remaining figures are organized so that engineers can refer to them directly in practice. So please verify the starting and target units and apply the correct multiplier.
This is the remaining part of the volume conversion table, containing conversion factors between US and imperial units such as quarts, gallons, and barrels. For example, to convert US gallons to liters, multiply by 3.78543, and a U.S. barrel for petroleum corresponds to 158.98 liters. The other values are provided for engineers to refer to as needed in the field. Please first find the base unit in the row and the target unit in the column, then apply the coefficient at the intersection for your calculation.
Finally, we have the flow rate conversion table. This table contains mutual conversion factors between various flow rate units, such as liters per minute or cubic meters per hour, and is structured using the principle of the multiplier where the row and column meet. For example, multiplying liters per minute by 0.06 converts it to cubic meters per hour, and multiplying cubic meters per hour by 35.314 results in cubic feet per hour. Since the other values are calculated in the same way, please find the unit combination you need for your work and apply the corresponding multiplier.
This slide is the volumetric flow rate conversion table, or volume rate equivalence. This table demonstrates the principle of converting different flow rate units using the multiplication coefficient at the intersection of the row and column. For example, when converting cubic feet per hour, you multiply by a coefficient such as 0.4719, and for U.S. gallons per minute, a coefficient such as 3.785 is applied. The remaining values are organized for engineers to refer to according to their practical needs. Please accurately identify the starting and target units, then multiply by the coefficient at the intersection to calculate the precise flow rate.
Next, this chunk summarizes the unit categories covered by the three conversion tables. First, area equivalence covers square feet, square miles, and square kilometers. Second, volume equivalence covers U.S. barrels, petroleum, cubic feet, U.S. quarts, U.S. gallons, and imperial gallons. Third, volume rate equivalence covers liters per hour, U.S. gallons per minute, U.S. barrels per day, and cubic feet per hour. Since all three tables use the same method of applying the multiplication factor at the intersection of rows and columns, once you understand the structure of the table, you can perform conversions in any of these areas: area, volume, or flow rate, in the same way.
Next, we turn to mass and pressure.
This slide is a mass conversion table for converting pounds to kilograms. It is based on the reference relationship that 1 pound equals 0.4536 kilograms. For example, 1 pound converts to 0.45 kilograms and 2 pounds to 0.91 kilograms. The remaining values are listed as they increase steadily according to the integer value of pounds. So please check the specific figures you need for your practical work. The usage is simple. First, find the pound value you wish to convert in the left column, then read and use the corresponding kilogram conversion value in the same row.
In this slide, we will look at the pressure equivalence table, which allows for the mutual conversion of various pressure units. This table is designed on the principle of converting units by multiplying the factor at the intersection of the row and column, and it includes a wide range of units from kilograms per square centimeter to kilopascals and feet of water. For example, when converting 1 kilogram per square centimeter to pounds per square inch, you multiply by 14.22. The remaining figures are organized so that engineers can refer to them directly whenever needed in the field. Please accurately identify the point where the row of the starting unit and the column of the target unit meet to use it in your calculations.
This table is a reference material summarizing conversion values between major pressure units, such as bar, inches of mercury, and kilopascals. For example, 1 bar corresponds to 29.53 inches of mercury, and 1 kilopascal converts to 0.01 bar. Rather than memorizing all the figures, please utilize this table when unit conversion is required in practice. First, find the reference unit you wish to convert in the row, and then identify and apply the value in the column of the corresponding conversion unit.
The following is a pressure conversion table that directly converts pounds per square inch to bar. For example, 1 pound per square inch corresponds to 0.068948 bar, and 10 pounds per square inch corresponds to 0.6894757 bar. Not all values are listed, so please find and apply the required pressure values directly from the table in your practical work. In particular, you can work more efficiently by using the conversion tip of moving the decimal point 2 places to the right to change bar to kilopascals, or one place to the left to change it to megapascals.
This slide is a continuation of the SI conversion table we looked at previously, providing more finely subdivided conversion values for the bar column. For instance, precise figures such as 0.275790 bar in the lower range or 1.03214 bar around 1 bar are listed. Rather than listing every value, I recommend that engineers look up the specific range needed during actual calculations. Since it is organized in detailed 1 pound per square inch intervals, it is advised to find the value immediately from the table and apply it precisely without separate interpolation calculations.
Next, we turn to temperature.
This slide is a reference table summarizing temperature conversion formulas frequently used in the field. For example, when converting Celsius to Fahrenheit, you multiply the Celsius value by 9/5 and then add 32. When converting Celsius to Kelvin, you add 273.16. The remaining formulas are also detailed in the table, so please check the units before and after conversion and then substitute the values into the corresponding formula. In the following pages, you can check a Celsius and Fahrenheit comparison table pre-calculated based on these formulas.
This slide shows the temperature conversion table for Celsius and Fahrenheit in the cryogenic range. It includes key conversion points such as absolute zero, where minus 273.16 degrees Celsius corresponds to minus 459.69 degrees Fahrenheit, and the point where minus 40 degrees Celsius and minus 40 degrees Fahrenheit are identical. You can compare the Celsius and Fahrenheit values on either side of the center column. The remaining detailed figures are arranged in close intervals of about 5 degrees, so please use this to quickly look up the temperature ranges needed in the field.
This slide is a continuation of the previous temperature conversion table, covering the ambient temperature range and the zero crossing point. You can verify the correlation between Celsius and Fahrenheit through examples such as the freezing point of water, where 0 degrees Celsius corresponds to 32.0 degrees Fahrenheit, and 20 degrees Celsius converting to 68 degrees Fahrenheit. The other values are finely subdivided around room temperature, so engineers should directly look up the required values using the side-by-side comparison structure during design or measurement. Please note the continued mark at the bottom of the table and refer to the high temperature range in the next part.
This is a reference table summarizing the conversion values between Celsius and Fahrenheit. It consists of a 3-column structure with the reference temperature in the center column and the corresponding Celsius and Fahrenheit values on either side. For example, the boiling point of water, 100 degrees Celsius, corresponds exactly to 212.0 degrees Fahrenheit, and 200 degrees Celsius in the high temperature range converts to 392.0 degrees Fahrenheit. Please look up the other detailed figures in the table as needed. For values not listed, you can calculate them precisely using the formula of multiplying Celsius by September 5th and adding 32.
This slide is a mutual conversion table for Fahrenheit and Celsius in the high temperature range. This table shows a linear relationship where both temperature scales increase together, with the structure placing Celsius and Fahrenheit values on either side of the central reference value. For example, 752.0 degrees Fahrenheit corresponds to 454.4 degrees Celsius, and 1022.0 degrees Fahrenheit converts to 537.8 degrees Celsius. For the remaining figures, engineers should first find the required temperature range in the center and then check the corresponding values on the left and right.
Following the previous table, this slide is a temperature conversion table covering the ultra-high temperature range, specifically the 2400s in Fahrenheit and the 700s in Celsius. For example, 704.4 degrees Celsius converts to 2372.0 degrees Fahrenheit, providing corresponding values for these extreme temperature ranges. Since not all figures are listed, engineers should first identify the temperature to be converted, and then find the necessary values in the Celsius and Fahrenheit columns. This data is useful when precise temperature conversion is required in extreme temperature environments of industrial processes.
This is the temperature conversion table for the high temperature range. Based on the conversion formula of subtracting 32 from Fahrenheit and multiplying by May 9th, This table shows a proportional relationship where Celsius increases by approximately 10 degrees for every 18-degree rise in Fahrenheit. For example, 2,462 degrees Fahrenheit converts to 787 degrees Celsius, and 2,534 degrees Fahrenheit converts to 810.0 degrees Celsius. Please use the remaining figures for quick comparison during high-temperature processes such as heat treatment or annealing.
Next, we turn to gravity and density.
Next, I would like to introduce the structure of the API and Boehme gravity table. This table consists of 5 columns. The first column is API gravity. The second is Boehme gravity. The third is specific gravity. The fourth is pounds per US gallon, lb/u.sgal. And the fifth is its reciprocal, US gallons per pound, US gal/lb. Both API and Boehme degrees are measurement scales used to express the specific gravity of liquids, and specific gravity refers to the ratio of the weight of oil at 60 degrees Fahrenheit to the weight of an equal volume of water. Using this table, you can convert the specific gravity of petroleum products and their weight per unit volume.
The following are the key values for the low specific gravity range of the API and Boehme gravity tables. This table shows the correlation between volume and weight according to changes in specific gravity. In particular, it illustrates an inverse relationship where the weight per gallon decreases and the volume per pound increases as the specific gravity decreases. For example, when the specific gravity is 1.0000, the weight per US gallon is 8.328 pounds, which serves as the reference point identical to water. The remaining values are organized so that engineers can refer to them directly when needed in practice. Please first check the measured specific gravity or API gravity, and then find the corresponding US gal/lb value to use in your design or calculations.
In this slide, we will look at the gravity table that covers the correlation between API gravity and specific gravity, as well as the reciprocal relationship between units. It demonstrates the principle that the higher the API gravity value, the lighter the oil and the smaller the specific gravity. For example, when the API is 25.83, the specific gravity is 0.8984. This table is designed to allow you to check the density characteristics of crude oil and petroleum products at a glance. Engineers should cross-reference the necessary values for actual field calculations, and please note that this is placed along with the continuation of the high-temperature conversion table discussed previously.
Finally, let's look at the concluding part of the temperature conversion table for the highest temperature range. This table covers the highest temperature interval from 2,552 degrees Fahrenheit to 2,732 degrees Fahrenheit. For example, values such as 2,552 degrees Fahrenheit or 815.6 degrees Celsius are presented as conversions at 18-degree intervals. For the remaining values, please refer directly to the Celsius or Fahrenheit temperature headers you wish to convert. As this is the final continuous section of the preceding conversion tables, it is recommended to use it for the final verification of the overall temperature conversion data.
In this slide, we will examine the structure of the API and Boehme gravity tables, which are petroleum gravity conversion tables. This table consists of 5 columns: API gravity, Boehme gravity, specific gravity relative to water, and weight conversion factors. For example, based on a specific API gravity value, you can immediately check the corresponding weight in lb/US gal or volume in US gal/lb. And Fahrenheit temperature values from 2642.0 to 2714.0 are also provided. Rather than memorizing all the values, please use this as a reference material by first selecting the gravity scale needed for actual design or calculation and then finding the appropriate conversion factor.
This table contains data for the API gravity range from 30.78 to 59.47, showing the characteristics of light petroleum where specific gravity and weight decrease as API gravity increases. For example, at an API gravity of 45.62, the specific gravity is 0.7972, and the weight per gallon is 6.637 pounds. Please refer to the remaining detailed values directly as needed for design or calculation. We recommend using this by observing how specific gravity, volume, and weight are linked and change based on the API gravity value.
This slide is a reference table covering the light petroleum range from API gravity 60.46 to 79.26. It shows the characteristic that the oil type becomes lighter as the specific gravity decreases. For example, at an API gravity of 70.35, the specific gravity is 0.6988 and the weight per gallon is 5.817 pounds. Engineers should refer to the detailed values as needed, and you can read the specific gravity, weight, and volume all at once from the same row if you know just one API gravity value. Please also utilize the relationship formulas between Baume degrees or API degrees and specific gravity listed at the end of the table.
In this slide, we have summarized the formulas that define the correlation between specific gravity, Baume degrees, and API degrees. Basically, both indicators have the same structure of placing a constant in the numerator, dividing by the specific gravity, and then subtracting a specific value. For example, Baume degrees are calculated by subtracting 130 from the value of 140 divided by the specific gravity. API degrees are similarly calculated by dividing 141.5 by the specific gravity and then subtracting 131.5. The remaining detailed formulas and inverse calculation methods are organized in the table, so please select the formula appropriate for your target, either API degrees, the petroleum industry standard, or Baume degrees, the general liquid scale, to convert the specific gravity index.
This slide contains the conversion formula between specific gravity and degrees Baume, along with the reference conditions used for the calculation. For example, the degrees Baume for liquids heavier than water is calculated by subtracting the specific gravity divided by 145 from 145. Here, specific gravity refers to the weight ratio of oil to water at 60 degrees Fahrenheit. The remaining detailed figures and measurement conditions are provided as reference data for engineers to use during practical calculations. Therefore, when an actual conversion is needed, please check the reference temperature and pressure conditions in this table to calculate the accurate value.
Next, I would like to introduce the method for determining the resulting gravity when mixing oils with different specific gravities. The density of the mixture D is calculated by dividing the sum of M times D1 and N times D2 by the sum of M and N. In this formula, D is the density or specific gravity of the mixture, M is the proportion of oil with density D1, and N is the proportion of oil with density D2. D1 and D2 represent the specific gravities of oil M and oil N, respectively. In other words, it is a method of calculating the weighted average of the specific gravities of the two oils based on their mixing proportions.
This table contains data for the final extension range of the API gravity table, from 80 to 99 degrees, showing the correlation between API gravity, specific gravity, and weight. For example, at 80.25 API, the specific gravity is 0.6659, and as the gravity increases to 99.05, the specific gravity drops to 0.6112. As shown, as the API gravity increases, the specific gravity and weight per gallon decrease, while the volume per pound increases. Engineers should first check the API gravity according to their design conditions and then refer to the corresponding specific gravity and unit weight values for their calculations.
Next, we turn to miscellaneous and index.
Now, I will introduce the other useful conversion tables from the Control Valve Handbook. This table organizes multiplication factors so that you can convert directly from one unit to another, and it consists of 3 columns. The first column is convert from, the unit before conversion. The second is to the unit after conversion. And the third is multiply by the factor to be multiplied. The usage is very simple. Just multiply the value before conversion by the factor listed and multiply by to get the value in the desired unit. Looking at the first row, there is an item for converting 1 cubic foot of methane gas to BTU, a unit of heat. In the case of methane, it corresponds to approximately 1,000 BTU. Please keep in mind that unlike the length or pressure conversion tables we saw earlier, which are a matrix format where rows and columns intersect, this table is a simple list of multiplication factors.
This slide is a reference table summarizing other conversion factors frequently used in practice, such as mass, volume, and properties of water. For example, converting 1 gallon of water to weight results in 8.336 pounds, and when converting kilograms to pounds, you can calculate it by multiplying by 2.205. The remaining figures in the table are organized so that engineers can look them up whenever needed during the design or calculation process. Please accurately verify the conversion direction and units for each item to ensure there are no errors in your practical calculations.
This slide is a conversion factor table that is useful when calculating power and gas flow rates. In the case of gas flow conversion, please note that the specific gravity is in the denominator, so the value varies depending on the type of gas. For example, when converting kilowatts to horsepower, you multiply by 1.341, and when converting standard flow based on air to propane, you multiply by 0.81. The remaining values are organized so that engineers can refer to them directly whenever needed in practice. When converting, please be sure to check the specific gravity of the target gas first and then apply the factor from the table for your calculations.
Next, I will introduce the table summarizing metric prefixes and symbols. This table defines multiplication factors and powers of 10 and their corresponding prefixes and symbols. For example, 10 to the 9th power is expressed as giga with the symbol G, and 10 to the minus 9th power is nano with the symbol N. Rather than memorizing all the values, please use this table to find the necessary factor and symbol to attach to the unit when you need to concisely express very large or small values during the design or calculation process.
In this section, I would like to introduce the notation rule for the subject index located at the end of the handbook. To use the index effectively, it is important to know what the font of the page number signifies. First, page numbers in bold indicate that a table is located at that position. Next, page numbers in italics indicate the location of a figure. Numbers in regular font point to the location where the content is explained in the main text. This is very convenient because you can immediately distinguish whether the information you're looking for is a table, a figure, or a text explanation just by looking at the font. Additionally, the first item in the index begins with entries related to the API or the American Petroleum Institute in alphabetical order.
This slide is the beginning of the subject index, organized so that you can quickly find content in the main text. In particular, please first familiarize yourself with the notation rule that bold text means a table and italics mean a figure. For example, the actuator item appears in several places from this page to page 172, and area equivalents can be found on page 266. The remaining items are organized by the same rules, so please find the necessary keyword in the index and refer to the related materials by checking the notation format of the corresponding page.
This slide is a reference table summarizing the detailed items of actuators and their related parts and design criteria. For example, the diaphragm type can be found on pages 8, 10, 61, and 172, and for each drive method, the direct acting type is described in detail on page 10. The remaining items are also matched to the corresponding pages by part and calculation formula. So when you need the specifications or sizing criteria for a specific part during the design process, please use this table to quickly find and utilize the relevant pages.
This slide is a reference table designed to help you quickly locate flange dimensions, standards organizations, and valve body items. For example, American pipe flange dimensions can be found on pages 251 and 252, and information on standards organizations like ASME is included on page 175. I recommend that engineers use the index to directly refer to other detailed dimensions, material designations, or specific types of valve bodies whenever needed during the design or review process. Please follow the page numbers for each item and carefully verify that they align with the latest versions of the relevant standards.
Finally, this is a reference table summarizing the detailed locations of items starting with bin. Ambient temperature corrosion is described on page 96, and backlash is detailed on page 2 and page 27. Since the remaining items are also organized by page in a granular manner, please use this table to quickly find the relevant pages when you need specific criteria or regional approval requirements in your practical work.
This slide is part of the subject index at the end of the handbook structured to help you quickly find the location of the main text by matching key terms with their corresponding pages. For example, the bow diagram can be found on pages 18 and 19, and bellows seals, a sub-item of the bonnet, are organized on pages 8, 9, and 51. The remaining items are structured in the same way, so please look up the necessary terms in alphabetical order and check the sub-items in detail to refer to the related content.
This slide is a reference table summarizing key technical terms starting with C and D and the pages where their detailed information is located. For example, you can find characteristic on page 3, and accessories for control valves are described in detail on page 67. Rather than listing every item, please use this index to find keywords first, and then navigate to the corresponding page whenever you need a specific definition or detailed specification during your work. In particular, for items like control valves or desuperheaters that are divided into subcategories, please be careful to refer to the pages for each specific type.
This slide contains index information regarding disks and electrical/electronic components, matching key technical terms with the pages where their details are located. For example, disk is on page 3, and equal percentage flow characteristic can be found on pages 3, 16, and 109. The remaining items are indexed in the same manner, so when you need to find the exact location of a specific part or characteristic value in practice, please use the keywords in this table to quickly navigate to the relevant page.
This slide is an index table summarizing key technical terms and their corresponding pages, focusing on flow characteristics and gain. For example, flow characteristic can be found on pages 59 and 108, and for gain, loop gain is described in detail on pages 5 and 34. The other items are also organized alphabetically so that engineers can quickly find the concepts they need during their work. Therefore, rather than memorizing the entire content, please refer to this index and check the detailed information on the corresponding pages when you need a specific parameter or calculation basis.
This slide is an index table summarizing key terms from the Control Valve Handbook, specifically items from H to I. For example, hunting, the phenomenon where a valve fails to stay in one position and oscillates, can be found on page 20, and the I/P item, which converts current to pneumatic pressure, is detailed on page 4. The remaining terms are also listed with their respective page numbers, so please use this index to quickly refer to the relevant pages whenever you need a definition or technical standard during your practical work.
This slide is a reference table organized to help you quickly distinguish between the inherent characteristics and installed characteristics of a valve. For example, the inherent characteristic, which refers to the properties of the valve itself, can be found on pages 4 and 31, while the installed flow characteristic, which refers to the properties after actual piping installation, is available on pages 4 and 17. Since the other items also have their corresponding pages specified next to each term, please use this table as a guide to find detailed definitions or standard specifications during the design or maintenance process.
This slide is an index table summarizing major technical items from L to N and their corresponding pages. For example, length equivalence can be found on page 263, and loop gain is detailed on pages 5 and 34. The remaining items are indexed in the same manner, so please refer to the relevant pages when you need specific conceptual definitions or conversion values during the design or calculation process.
This slide is a reference table organizing the locations of key items related to noise control. For example, you can find noise abatement trim on pages 141 and 143, and hydrodynamic noise prediction is listed on page 140. The remaining items are also organized alphabetically. So if there are specific technical standards or certification procedures you need during your work, please use the keywords to find the corresponding pages.
This slide is a reference table summarizing where major components and design factors, including packing and positioners, are located in the textbook. For instance, information on packing friction can be found on pages 27 and 131, and the various types of positioners are described in detail on page 67. Rather than listing every item, please use this table to find the keyword first when you need detailed specifications or calculation factors for a specific part, and then proceed to the relevant page.
This slide is an index table organizing the page locations of items frequently referenced during design and calculation processes, such as pressure conversion, steam properties, and valve characteristics. For example, the pressure conversion table can be quickly found on page 268, and saturated steam properties on page 212. Instead of memorizing all the items, if you need specific physical properties or conversion factors during actual calculations or specification reviews, please find the item in this table and refer to the corresponding page.
This slide is a reference table summarizing key components and performance items from R to S. For example, resolution, which is the smallest detectable change, can be found on page 5, and the sizing coefficients used for valve capacity calculations are on page 125. Other items are also listed in detail along with their respective page numbers. Engineers should use this index to directly locate the relevant pages whenever detailed specifications or calculation bases for specific components are needed during design or maintenance.
This slide is an index table for steam conditioning, conversions, and trim items. You can quickly check which pages of the manual contain each component and key concept. For instance, steam conditioning valves for regulating steam conditions are on page 162, and details on trim, which determines the flow rate, can be found on pages 6 and 11. Since the remaining items are also organized alphabetically, please refer to the relevant pages using these keywords when specific formulas or standards are required during design or maintenance.
This chunk is the final part of the handbook index, providing a reference table of key terms sorted alphabetically with their corresponding page numbers. In particular, the valve body items are very granular. For example, double-ported options can be found on pages 11 and 44. Other items are also detailed by capacity, guiding characteristics, and body components. Rather than memorizing everything, please use this as a reference guide to quickly navigate to the correct page by searching for key terms alphabetically during actual design or maintenance work.
Next, here is a reference table organizing the remaining index items. You can find the pages for various instrumentation terms, conversion tables, and sizing locations based on fluid type, as well as plug guiding methods. For example, for valve sizing, compressible fluids are listed on page 118, and liquids are on page 110. Rather than listing every item, please use this index table to quickly locate the specific concepts or conversion values you need during your practical work.